we're continuing to explore our spherical coordinates. I want to start by just taking this point that I gave us in rectangular coordinates and figuring out what rho, theta, and phi would be. So I think probably the simplest one to figure out is rho, because that's simply the distance from the origin. So rho would be the square root of -2 squared plus -2 squared plus -1 squared. Let's see, that's the square root of 4 plus 4 plus 1. That's the square root of 9. Oh, that's lovely. That's just 3. Okay. Now theta, I'm used to working with just in cylindrical coordinates. So I can just work in the xy plane. I'm going to plot the point -2, -2. So I know that theta has to be some angle that's going to put me here in quadrant 3. Now I also know, which I can see from here, that tangent of theta will be y over x. I can see that from this triangle, or I can see that basically here tangent's going to be negative, and then I can just use my reference angle alpha, and this would be 2 over 2. Okay. So I've got that tangent of theta is equal to -1. That means that tangent of alpha, my reference angle, is the absolute value of that, so that's just 1. So alpha would be pi over 4. That's the acute angle that has a tangent of 1. So theta, the simplest choice for theta, would just be pi plus pi over 4, which would be 5 pi over 4. Okay, so all that's left is for us to get phi. Okay. So in figuring out phi, I'm going to be working with this triangle here. And remember, we decided that it was most helpful to work with cosine, because phi is taking on values between 0 and pi, and inverse cosine also takes on values just between 0 and pi. So what I know is that cosine of phi is just going to be z over rho. Phi is going to be arc cosine then of z over rho. And so that's going to be arc cosine of -1, because our z was -1, and we just figured out that rho was 3. Now, if that was cosine of one of our nice angles, pi over 3, pi over 4, or pi over 6, I would expect you to evaluate it. It's not, so we simply leave that as arc cosine of -1/3. You'll notice, because the cosine is negative, this is going to be an obtuse angle. That makes sense because our z value was negative. So that said, if we started pointing straight up, in order to get down to a negative value, we would have to rotate past pi over 2. So those two will always go hand in hand. Z will be negative when phi is obtuse. Okay, or when phi is pi. Okay, because of course, cosine of pi is -1. Okay, next thing I want to take a look at is our constant surfaces. Okay. So if I have rho is constant, okay, let's just call it c, what does that look like? Well, that's saying that the distance from the origin is constant. I know what that means. That's going to mean that I have a sphere of radius c centered at the origin. So, if rho is constant, this is the constant surface that we're going to get. We're going to have a lovely sphere. And that's actually why this is called spherical coordinates. The rho value essentially tells me, if I know the rho value of a point is 2, and this is the sphere of radius 2, that tells me my point is somewhere on this sphere. To narrow down exactly where it is, I need to know my theta and my phi. Now, if we look at theta being constant, for that, let's suppose here we've got our x, y, and z axis. Now, if I rotate a certain amount theta in the xy plane, okay, so the pencil is representing that I've rotated, it looks like about pi over 4 is what I've chosen for this example. theta has to stay pi over 4, but rho isn't fixed. So you want to imagine that this pencil that's determining this ray is infinitely long in this direction. It does stop at the origin because rho can't be negative, but I've got this infinitely long pencil. Okay. And then phi is also allowed to vary. So right now, if I'm on the xy plane, phi would be pi over 2. But phi could be 0 all the way down to pi. What that's doing is that's sweeping out a half plane. Okay. So it's just like what we had when we were working in cylindrical coordinates. If theta is constant, we're going to get a half plane. Okay. So then what happens if phi is constant? Okay. Well, I want to take a look at some specific examples for this. If phi is, let's say phi is pi over 6. Let's take a look at that. Okay. So I'm rotating down pi over 6 from the positive z-axis. Now again, rho is free to be anything we want that's not negative. So we're imagining that this is an infinitely long pencil, but that it does in fact stop at the origin. Okay. Theta is free to be whatever we want. So I've got to keep this angle of pi over 6 with the z-axis, but I can rotate around the z-axis however I like. So what that's going to give me is a half cone. Now, I'm going to call that a half cone because as we saw when we were doing quadric surfaces, if I had an elliptic cone, there would be a mirror image of this down here. Okay. So most of the time, if phi is constant, I'm going to get a half cone. But there are a few special cases, so I'm just going to say usually. Okay. If phi is equal to 0, I'm going to actually just get, in that case, we're pointing straight up. I can rotate, but that doesn't sweep out any additional area. If phi is 0, I'm just getting the non-negative z-axis. Similarly, if phi is equal to pi, we'd be pointing straight down, and so we'd be getting the non-positive z-axis. Now I can sort of think of those as cones. They're just cones that got really skinny. They got so skinny that they collapsed down to just a single ray. Okay. The other special case that we get is what if phi is pi over 2? So let's take a look at that. If phi is equal to pi over 2, that would mean I had rotated down so that I was on the xy plane. Okay. I'm on the xy plane, but theta can be whatever it wants to be, and rho can be whatever non-negative number it wants to be. That's going to sweep out the entire xy plane. Now I can sort of think of that as a cone. It's just a cone that was getting wider and wider and wider, and it got so wide that it completely flattened out and became a plane. This is the standard way to represent a plane. It's as a parallelogram. A lot of times when we get to spherical coordinates, people want to start representing planes as disks because they're thinking, oh, okay, I'm rotating down to the xy plane and then I can sweep out whatever area I want. You're visualizing it as a disk. I understand that thinking. It makes total sense. It's totally correct. It's just not the convention. The convention is when you draw a disk, it's understood to represent a finite area. When you draw a parallelogram, that sometimes represents a finite parallelogram, but that's the way we represent an infinite plane. All right, so those are our constant surfaces. a sphere, a half plane, or a half cone, including the degenerate half cones that are either so skinny that they're just a single ray or so fat that they're a flattened entire plane.